Close your eyes for a moment. Imagine nothing. Not darkness. Not empty space. Not silence. True nothing. No time ticking forward. No space stretching outward. No matter. No energy. No laws of physics waiting to spring into action. Just nothing. Can you picture it? You can't. Your brain won't let you. Because even when you try to imagine emptiness, you're imagining something. A void. A blank canvas. But before the universe existed, there wasn't even a canvas. And then, in an instant so brief it defies comprehension, everything changed. 13.8 billion years ago, the entire universe, every galaxy, every star, every planet, every atom in your body, burst into existence. Not in a place, not at a time, but as the very beginning of place and time themselves. This is the story of how it all began. The story of the first heartbeat of existence. The story of how nothing became everything. This is the story of the birth of the universe. Before we dive into what happened, we need to wrestle with something that sounds simple but is actually the hardest question you'll ever try to answer. What existed before the beginning? Your instinct is probably to say nothing, and you'd be right. But what does nothing really mean? When you walk into an empty room, you might say there's nothing there. But that's not true. There's air. There are particles of dust floating in beams of sunlight. There are electromagnetic waves passing through, radio signals, Wi-Fi, maybe even radiation from distant stars. There's the floor beneath your feet and the walls around you. There's space itself, the three-dimensional stage where everything plays out. Strip all of that away. Take out the air. Remove every particle. Turn off every wave of energy. Now you have empty space, right? A vacuum. But even a vacuum in our universe isn't truly nothing. It still has properties. Can bend and warp. Quantum particles can pop in and out of existence within it. It's governed by laws of physics. It has dimensions, length, width, height. And most importantly, it has time moving through it. But before the universe existed, there was no space to be empty. There were no dimensions to measure. There was no time to flow forward. The laws of physics didn't exist yet because there was no universe for them to govern. Think about time for a second. Right now, you experience time as a river flowing in one direction. The past is behind you. The future is ahead. Every moment leads to the next. But time itself is part of the fabric of the universe. It's woven together with space in what Einstein showed us is a single entity. Space-time. So asking what happened before the Big Bang is like asking what's north of the North Pole? The question itself doesn't make sense. There is no before when time doesn't exist yet. There is no where when space hasn't been created. And yet, somehow, the universe began. Philosophers have struggled with this for thousands of years. Ancient thinkers asked, did the universe have a beginning, or has it always existed? If it had a beginning, what caused it? And what caused the cause? For most of human history, we had only stories and guesses. Different cultures created different myths. Some imagined the universe hatching from a cosmic egg. Others pictured it emerging from chaos or being spoken into existence by gods. These stories gave meaning and comfort, but they weren't explanations in the scientific sense. Then, in the 20th century, something remarkable happened. Scientists started to find actual evidence. Real clues hidden in the fabric of space itself. And what they discovered was stranger and more beautiful than any myth. But to understand what they found, we need to talk about what people mean when they say the Big Bang. If you've heard of the Big Bang before, you probably picture a massive explosion. A cosmic bomb going off in the darkness of space, sending matter flying outward in all directions. That image is completely wrong. The Big Bang wasn't an explosion that happened somewhere in space. It was the birth of space itself, and time, and matter, and energy, all at once. Imagine a balloon with dots drawn on it to represent galaxies. Now imagine deflating that balloon until it's impossibly tiny. Smaller than a grain of sand, smaller than an atom, smaller than anything you can measure. At that point, the dots aren't just close together. They don't exist yet as separate things. Everything is compressed into a single point of infinite density and temperature. Scientists call this a singularity. Now imagine the balloon starting to inflate. The rubber of the balloon represents space itself. As it expands, the dots move apart from each other. But here's the key. The dots aren't moving through space. The space between them is growing. They're being carried apart by the expansion of the balloon itself. This is what happened at the Big Bang. The universe didn't explode into empty space. Space itself began expanding, and it's been expanding ever since. But who figured this out? And how? The story starts in the early 1900s with a Belgian priest and physicist named Georges Lemaitre. While most scientists at the time believed the universe was static and eternal, Lemaitre studied Einstein's equations of general relativity and came to a shocking conclusion. The universe must be either expanding or contracting. Couldn't stand still. Lemaitre proposed that if the universe is expanding now, then if you run time backward, everything must have been closer together in the past. Run the clock back far enough, and the entire universe would have been compressed into what he called a primeval atom, a state of unimaginable density where everything began. At first, many scientists mocked the idea. The British astronomer Fred Hoyle dismissively called it the Big Bang during a radio broadcast, trying to make it sound ridiculous. The name stuck, even though it's misleading. But Lemaitre was onto something profound. Then came more evidence. In 1929, an American astronomer named Edwin Hubble made one of the most important discoveries in the history of science. He was studying distant galaxies through the most powerful telescope of his time, and he noticed something strange. Almost all galaxies were moving away from us. And the farther away they were, the faster they were moving. This is exactly what you'd expect if space itself was expanding. Imagine those dots on the balloon again. From the perspective of any dot, all the other dots appear to be moving away. And dots that are farther apart separate faster as the balloon inflates. Hubble's discovery was the first solid evidence that the universe had a beginning. If everything is moving apart now, then everything must have been together in the past. Wind back the clock far enough, and you reach that moment of creation. But what actually happened in that moment? What were the first seconds of existence like? To answer that, we need to travel back to the very beginning. To a time so early that the word time barely applies. To the first instant of everything. The universe is now exactly 0 seconds old. Except that's not quite right, because you can't even say 0 seconds when time doesn't exist yet. Scientists have calculated that there's a limit to how far back we can trace the history of the universe. It's called Planck time, and it's about 10 to the power of minus 43 seconds. That's a decimal point followed by 42 zeros and then a 1. It's so small that nothing shorter has any meaning in physics. We don't know what happened before Planck time, or even if before makes sense. Our laws of physics break down. General relativity, which describes gravity and spacetime, stops working. Quantum mechanics, which describes the behavior of tiny particles, stops working. We need a theory that combines both, something called quantum gravity, and we don't have that yet. But starting from Planck time, we can describe what happened with reasonable confidence. The entire universe is unimaginably small. Everything that will ever exist, all the galaxies, all the stars, all the planets, all the vast stretches of space, is compressed into a region smaller than a single atom. The temperature is beyond comprehension, about 10 to the power of 32 degrees. Hot enough that matter as we know it can't exist. There are no atoms, no protons, no neutrons. Just pure energy boiling in a soup of fundamental particles and forces. And then, something extraordinary happens. In a fraction of a second so small it makes a blink of an eye seem like an eternity, the universe explodes in size. This event is called cosmic inflation, and it's one of the most mind-bending concepts in modern physics. In less than 10 to the power of minus 32 seconds, the universe expands by a factor of at least 10 to the power of 26. It doubles in size, then doubles again, then again, then again, over and over in rapid succession. A region smaller than a proton becomes larger than a galaxy. Maybe larger than the entire observable universe we see today. Why did this happen? The best explanation is that the universe was filled with a special kind of energy field, something physicists call the inflaton field. This field was in an unstable, high-energy state, and as it started to settle down, it released its energy in the form of explosive expansion. Think of it like a ball balanced on top of a hill. For a moment it sits still. Then it starts to roll down, picking up speed, releasing potential energy as motion. The inflaton field rolled down from its high-energy state, and that energy drove the expansion of space itself. Inflation solves several puzzles about our universe. It explains why the universe looks almost the same in every direction. It explains why space seems flat rather than curved. And it explains how tiny quantum fluctuations, random microscopic ripples in the fabric of space, got stretched out to cosmic sizes, eventually becoming the seeds that grew into galaxies. But cosmic inflation is just the opening act. When inflation ends, the universe is still incredibly small by everyday standards, but it's vastly larger than it was. And it's still extraordinarily hot. The energy from the inflaton field doesn't just disappear. It converts into matter and radiation. The universe fills with a dense, hot soup of fundamental particles. At this point, we're about a billionth of a second into the history of the universe. The temperature has dropped, if you can call 10 trillion degrees dropping, to a point where quarks can exist. Quarks are the building blocks of protons and neutrons, but they don't form those particles yet. It's too hot. They're swimming freely in what scientists call a quark-gluon plasma. Then, as the universe continues to expand and cool, something crucial happens. Quarks start to stick together. 3 quarks combine to make a proton. 3 different quarks combine to make a neutron. Within the first second of the universe's existence, we have the nuclei of the simplest atoms beginning to form. But there's a mystery here that might trouble you. If matter and antimatter are created in equal amounts, and they should be, according to the laws of physics, why is the universe made of matter? Where did all the antimatter go? When a particle of matter meets its antimatter counterpart, they annihilate each other in a burst of energy. So in the early universe, protons collided with antiprotons, electrons smashed into positrons, and both vanished in flashes of light. For every billion particle pairs that destroyed each other, only one matter particle survived. That tiny imbalance, for reasons we still don't fully understand, is why you exist. Why anything exists. If the universe had been perfectly symmetric, matter and antimatter would have completely annihilated each other, leaving nothing but a sea of light. But somehow matter won, just barely, and that leftover matter became everything we see. As the universe continues to expand, it cools further. After about 3 minutes, the temperature has dropped to 1 billion degrees, cool enough for protons and neutrons to stick together and form the nuclei of simple elements. Mostly hydrogen, which is just a single proton, some helium, which is 2 protons and 2 neutrons, and tiny traces of lithium. This process is called Big Bang nucleosynthesis, and it's one of the major pieces of evidence for the Big Bang theory. When scientists measure the abundance of these elements in the universe today, they find exactly the ratios that the Big Bang theory predicts. It's like finding a fingerprint that matches perfectly. But the universe isn't done transforming yet. In fact, one of the most important moments is still to come. After 3 minutes, we have atomic nuclei. But we don't have atoms yet. That might sound strange, but here's the difference. An atom is a nucleus surrounded by electrons. And for electrons to settle into stable orbits around nuclei, the universe needs to be cool enough that photons, particles of light, don't immediately knock them loose again. For hundreds of thousands of years, the universe is filled with a fog of charged particles. Electrons and nuclei swim through space, and photons bounce between them constantly, scattering in every direction. Light can't travel in straight lines. It's like trying to see through a thick cloud. The universe is opaque. Then, about 380,000 years after the Big Bang, the temperature drops below 3,000 degrees. This is a magic threshold. Electrons start to bind to nuclei, forming the first complete atoms. Mostly hydrogen, some helium, and suddenly the universe becomes transparent. Photons that had been scattering endlessly off charged particles are suddenly free to travel. Light can finally move through space without being absorbed or bounced away. This moment is called recombination, and it's when the universe lets out its first clear light. Those photons are still traveling through space today. They've been stretched and cooled by the expansion of the universe, but they're still here all around you right now. They form what scientists call the cosmic microwave background, or CMB. In 1964, two scientists named Arno Penzias and Robert Wilson were testing a sensitive radio antenna in New Jersey. They kept picking up a strange hiss of static that seemed to come from every direction in the sky. At first, they thought it was interference. They even cleaned pigeon droppings out of the antenna, thinking that might be the problem. But the signal remained. What they discovered was the afterglow of the Big Bang itself. The light from recombination cooled over billions of years into microwave radiation. This discovery won them the Nobel Prize and gave us one of the most powerful pieces of evidence that the Big Bang really happened. Today, we've mapped the CMB in exquisite detail using satellites like COBE, WMAP, and Planck. When you look at these maps, you're seeing a snapshot of the universe when it was just 380,000 years old. You're seeing the tiny temperature fluctuations that correspond to slightly denser and slightly less dense regions. And those dense regions? They're the seeds of all the galaxies, stars, and planets that will eventually form. But at this point in the universe's history, there are no stars yet. No galaxies. No planets. Just expanding clouds of hydrogen and helium gas, drifting through the darkness. The universe enters what scientists call the Dark Ages. For hundreds of millions of years, there's nothing to see. No stars to light the void. Just cold gas spreading out as space continues to expand. But gravity is patient, and it's been working this whole time. Gravity doesn't care how spread out things are. It doesn't care how fast the universe is expanding. It pulls. Slowly, relentlessly, it pulls. In the regions where the gas is slightly denser, the seeds planted during inflation and visible in the CMB, gravity draws more gas in. Dense regions get denser. They start to collapse under their own weight. And as they collapse, they heat up. Imagine compressing a gas. The molecules get closer together. They collide more often. The temperature rises. This is basic physics, the same reason a bicycle pump gets warm when you use it. In the collapsing clouds of the early universe, the temperature at the core rises higher and higher. After millions of years of collapse, the center of the cloud reaches 10 million degrees. At this temperature, something remarkable happens. Hydrogen nuclei, which are just single protons, start slamming into each other with enough force to overcome their electrical repulsion. When they collide, they can fuse together, creating helium. And when that happens, a tiny bit of mass converts into energy according to Einstein's famous equation, E equals mc squared. That energy is released as light and heat. The core of the cloud starts to shine. Pressure builds up, pushing outward, balancing the inward pull of gravity. The collapse stops. The cloud stabilizes. A star is born. The first stars in the universe weren't like our sun. They were monsters. Without any heavy elements to help them shed heat, these early stars formed from pure hydrogen and helium, and they grew enormous. Some were hundreds of times more massive than the sun. They burned brilliantly but briefly, living only a few million years. And when they died spectacularly. The most massive stars ended their lives in supernova explosions. Blasts so powerful they outshine entire galaxies for a few weeks. In the furnace of these explosions, the intense heat and pressure forged new elements. Carbon, oxygen, silicon, iron, gold, uranium. Every element heavier than hydrogen and helium was created in the cores of stars or in the shock waves of their deaths. When a supernova explodes, it scatters these newly made elements into space. The gas clouds that will form the next generation of stars are now enriched with carbon and oxygen and iron. Those stars will have planets. Rocky planets with metal cores. Planets with water. Planets where chemistry can become complex. Planets where life can begin. But we're getting ahead of ourselves. The first stars didn't just create elements. They created structure. Gravity pulled stars together into groups. Those groups merged into larger clusters. The clusters formed galaxies, vast islands of hundreds of billions of stars, held together by gravity, separated by even vaster stretches of empty space. The early galaxies were small and chaotic. They collided and merged frequently. Over billions of years, they grew into the majestic spiral and elliptical galaxies we see today. The Milky Way, our home galaxy, formed from the merger of dozens of smaller galaxies over billions of years. And at the center of almost every galaxy, something strange lurks. A supermassive black hole, millions or even billions of times the mass of the Sun. We still don't fully understand how these giants formed so early in the universe's history, but they seem to play a crucial role in shaping galaxies. By the time the universe is a few billion years old, it's transformed from a smooth, featureless fog into a cosmic web of galaxies, clusters, and filaments, separated by enormous voids. It's beginning to look like the universe we see around us today. But our story isn't complete, because we haven't yet arrived at the birth of our own solar system, the place where this whole cosmic journey becomes personal. 4.5 billion years ago, in a quiet spiral arm of the Milky Way galaxy, there's a cloud of gas and dust. It's not special. Thousands of clouds like it drift through the galaxy. This one is a few light-years across, made mostly of hydrogen and helium, but also enriched with heavier elements from the deaths of earlier generations of stars. Something disturbs the cloud. Maybe a nearby supernova sends a shock wave through it. Maybe it passes through a denser region of the galaxy. Whatever the trigger, part of the cloud starts to collapse. The process is the same as the formation of the first stars, but this time something different happens. As the cloud collapses and spins, it flattens into a disk. Most of the mass falls into the center, heating up, eventually igniting nuclear fusion. The Sun is born, but about 1% of the mass stays in the disk, orbiting the young star. And in that disk, dust grains start to stick together. At first, it's just gentle collisions. Static electricity and weak chemical bonds hold tiny particles together. Grain by grain, they build up. Pebbles form, then boulders, then mountains of rock and ice, tumbling through the disk. These growing objects, called planetesimals, have enough gravity to attract more material. The bigger they get, the faster they grow. It's a runaway process. Over millions of years, planetesimals collide and merge, forming larger and larger bodies. Close to the Sun, where it's hot, only materials with high melting points can condense. Rock and metal. These regions form the rocky planets: Mercury, Venus, Earth, and Mars. Farther out, beyond what we call the frost line, it's cold enough for water to freeze. Ice is much more abundant than rock in the disk, so the planets that form here can grow much larger. They become the gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune. Earth forms from countless collisions. Asteroids and planetesimals crash into the growing planet, delivering not just rock and metal, but also water and organic compounds. The young Earth is a hellish place. Molten rock, constant bombardment, an atmosphere of toxic gases. Then, about 4.5 billion years ago, disaster strikes. A Mars-sized object crashes into Earth. The impact is so violent it vaporizes rock, sending debris into orbit. That debris coalesces to form the Moon. But that catastrophe also does something crucial. Tilts Earth's axis, giving us seasons. It leaves Earth with enough mass and gravity to hold onto an atmosphere. And it mixes the planet's interior, helping to drive plate tectonics, which will eventually be essential for maintaining a stable climate. Over hundreds of millions of years, Earth cools. The crust solidifies. Water vapor condenses, falling as rain for perhaps thousands of years, filling the first oceans. Asteroids and comets continue to bombard the surface, but they're also delivering precious cargo: water, amino acids, the chemical building blocks of life. Somewhere in those early oceans, perhaps in a warm tidal pool, perhaps around a deep-sea volcanic vent, chemistry becomes biology. Simple molecules start to copy themselves. They compete for resources. They evolve. And life begins its long journey from single cells to the incredible diversity we see today. But none of this, not Earth, not the Sun, not the Milky Way, not even the atoms in your body, would exist without the Big Bang. Every atom of carbon in your muscles was forged in the core of a dying star. Every atom of calcium in your bones was created in a supernova explosion. The iron in your blood, the oxygen you breathe, the silicon in the ground beneath your feet. All of it was made in stars that lived and died billions of years ago. You are, quite literally, made of stardust. The universe spent 13.8 billion years creating you. But how do we know all this really happened? How can we be sure the Big Bang wasn't just a clever story scientists made up? Science isn't about believing stories. It's about evidence. And the evidence for the Big Bang is overwhelming. Let's start with the most direct observation. The universe is expanding. Remember Edwin Hubble's discovery? He found that distant galaxies are moving away from us. But how did he know they were moving? The answer lies in something called redshift. When an object emitting light moves away from you, the light waves get stretched out. This makes the light appear redder than it should be. It's similar to the Doppler effect you hear when an ambulance drives past. The siren sounds higher-pitched as it approaches and lower as it moves away. Hubble measured the light from distant galaxies and found that almost all of them were redshifted. The farther away a galaxy was, the more redshifted its light, meaning the faster it was moving away. This is exactly what you'd expect from an expanding universe. Since Hubble's time, we've measured this expansion with incredible precision. We can now trace the expansion backward and calculate when everything was together, about 13.8 billion years ago. Then there's the cosmic microwave background. This afterglow of the Big Bang is everywhere. No matter which direction you look in the sky, you see it. And its properties match the predictions of the Big Bang theory with stunning accuracy. When scientists analyzed the tiny temperature fluctuations in the CMB, they found patterns that match exactly what you'd expect from sound waves traveling through the early universe. These patterns tell us the age of the universe, the density of matter, the amount of dark energy, and even the curvature of space. All of these measurements are consistent with the Big Bang model. Another piece of evidence is the abundance of light elements. Remember Big Bang nucleosynthesis? The theory predicts exactly how much hydrogen, helium, and lithium should have been created in the first few minutes. When astronomers measure the oldest stars and gas clouds in the universe, they find these elements in precisely the predicted ratios. There's no other explanation for why the universe is about 75% hydrogen and 25% helium. We can also see the evolution of galaxies over time. When we look at distant galaxies, we're looking back in time because their light has taken billions of years to reach us. And what we see matches the predictions. Galaxies in the early universe are smaller, more irregular, and contain fewer heavy elements than galaxies today. We're watching the universe grow up. All of these independent lines of evidence point to the same conclusion. The universe had a beginning. It was hot and dense. It expanded and cooled. Stars formed. Galaxies assembled. And here we are. But here's where things get even stranger. If the universe had a beginning, what came before? This is the question that keeps physicists awake at night. One possibility is that before the Big Bang simply doesn't exist as a concept. Time itself began with the Big Bang, so asking what came before is like asking what's north of the North Pole. The question is meaningless. But some physicists aren't satisfied with that answer. They've proposed ideas that are so strange they sound like science fiction. One idea is the cyclic universe. Imagine the universe expanding from a Big Bang, then eventually collapsing back in on itself in a big crunch. At the moment of maximum compression, it bounces, creating a new Big Bang, and the cycle repeats forever. Big Bang, expansion, collapse, big crunch, Big Bang again. The universe has no true beginning or end, just an eternal cycle of death and rebirth. There are mathematical models that support this idea, but there are also problems. Each cycle would create more entropy, more disorder, and it's hard to see how that could continue forever. Still, it's an intriguing possibility. Another idea is the multiverse. This suggests that our Big Bang wasn't the only one. There could be countless other universes, each with its own Big Bang, its own laws of physics, its own history. These universes might be completely separate from ours, unreachable and undetectable. Or they might exist in extra dimensions we can't perceive. In some versions of this idea, new universes are constantly budding off from existing ones. Regions of space undergo inflation and become new universes. It's an infinite cosmic landscape of bubble universes, each one a separate reality. Or consider quantum fluctuations. In quantum mechanics, particles can pop in and out of existence spontaneously, borrowing energy from the vacuum for a brief moment before disappearing again. Some physicists have suggested that the entire universe could be the ultimate quantum fluctuation, a random blip that happened to expand into all of reality. The famous physicist Stephen Hawking proposed something even stranger. Using ideas from quantum mechanics and general relativity, he suggested that asking what happened before the Big Bang is like asking what's south of the South Pole. At the moment of the Big Bang, time itself becomes more like space. The usual distinction between past and future breaks down. Time becomes imaginary, not in the sense of being fake, but in the mathematical sense. The universe, according to Hawking, has no boundary in time, no beginning point where you can stand and say, "This is where it all started." These ideas are fascinating, but here's what's important to remember. They're speculative. Unlike the Big Bang theory itself, which is supported by mountains of evidence, these ideas about what came before are largely untestable with current technology. They're more like educated guesses than established science. We may never know what came before the Big Bang, or if before even makes sense. And that's okay. Science is comfortable with uncertainty. It's comfortable saying, "We don't know yet." But there's another question that haunts us. If the universe had a beginning, will it have an end? The ultimate fate of the universe depends on two things: how much matter and energy it contains, and how fast it's expanding. For most of the 20th century, scientists thought the expansion of the universe should be slowing down. Gravity pulls everything together, so it should act as a brake on the expansion. The question was whether there was enough matter to eventually halt the expansion and cause the universe to collapse, or whether it would expand forever, just gradually slowing down. Then, in 1998, two teams of astronomers made a shocking discovery. They were studying distant supernova explosions, using them as markers to measure how the expansion of the universe has changed over time. What they found stunned everyone. The expansion of the universe isn't slowing down. It's speeding up. Something is pushing the universe apart, overcoming the pull of gravity. Scientists call this mysterious force dark energy, but that's just a name for our ignorance. We don't know what it is. It makes up about 68% of the total energy in the universe, but it's completely invisible and undetectable except through its gravitational effects. If dark energy continues to dominate, the universe will expand forever, faster and faster. This leads to what scientists call the Big Freeze or heat death. In this scenario, galaxies will move farther and farther apart. Eventually, they'll be so far away that their light can't reach us anymore. The night sky will go dark. Stars will continue to form for a while, but they'll burn through all the available hydrogen. New star formation will stop. Existing stars will die. The universe will fill with cold, dead remnants. White dwarfs, neutron stars, black holes. These objects will slowly decay over unimaginable timescales. Protons themselves might eventually fall apart, turning all matter into radiation. After 10 to the power of 100 years, a 1 followed by 100 zeros, even black holes will evaporate through a process called Hawking radiation. The universe will become a thin, cold soup of photons and fundamental particles, spread across an ever-expanding void. Everything will reach the same temperature, just a tiny fraction above absolute zero. Nothing will ever happen again. It's a bleak picture, but it's also incomprehensibly far in the future. The Sun has another 5 billion years before it dies. The Milky Way will collide with the Andromeda Galaxy in about 4 billion years, forming a new, larger galaxy. Stars will continue to light the universe for trillions of years. But there are other possibilities. If dark energy grows stronger over time, something that's possible in some theoretical models, it could eventually become powerful enough to tear apart galaxies, then solar systems, then planets, then atoms themselves. This is called the Big Rip. Space would expand so rapidly that the forces holding matter together couldn't compete. Everything would be shredded into fundamental particles in a final moment of destruction. On the other hand, if dark energy is temporary, or if it reverses, gravity could eventually win. The expansion could slow, stop, and reverse. The universe would start to contract. Galaxies would collide and merge. The cosmic microwave background would heat up, eventually becoming hot enough to vaporize stars. Everything would fall back together in a big crunch, the opposite of the Big Bang. The universe would end as it began, in a state of infinite density and temperature. There's even a stranger possibility called vacuum decay. This idea suggests that the universe might be in a false vacuum state, like a ball balanced on a ledge, seemingly stable but not in the lowest energy state possible. If the universe tunnels to a lower energy state, a bubble of true vacuum would form somewhere and expand at the speed of light. Inside that bubble, the laws of physics would be different. Atoms couldn't exist. When the bubble reached you, you'd be destroyed instantly, transformed into exotic particles governed by alien physics. The good news? If this is going to happen, there's no way to see it coming, and no way to stop it. And it might not happen for billions or trillions of years, if at all. Which scenario is correct? We don't know. The fate of the universe depends on the nature of dark energy, and we're only beginning to understand what that is. But here's what strikes me as beautiful about all of this. Even in the face of cosmic death, even knowing that everything might eventually end in cold darkness or violent destruction, the universe gave rise to you, to consciousness, to beings who can look up at the stars and understand where they came from, who can trace the history of existence back to its first moment and forward to its last. That's extraordinary. Let's zoom out for a moment and think about what we've covered. 13.8 billion years ago, the universe began, not as an explosion in space, but as the beginning of space and time themselves. In the first fraction of a second, it underwent cosmic inflation, expanding faster than you can imagine. In the first 3 minutes, it forged the light elements. After 380,000 years, it became transparent, releasing the light we now see as the cosmic microwave background. Over hundreds of millions of years, gravity pulled gas into clumps. The first stars ignited, lived briefly, and died in supernova explosions, scattering heavy elements into space. Those elements became part of new stars, new planets. Galaxies assembled from smaller pieces, growing into the majestic structures we see today. 4.5 billion years ago, in one particular galaxy, a cloud of gas collapsed to form a star we call the Sun. Around it, a disk of dust and debris coalesced into planets. One of those planets, orbiting at just the right distance to have liquid water, developed the conditions for life. And here you are. Every atom in your body was forged in the heart of a star. The carbon that makes up your cells, the oxygen you breathe, the iron in your blood, all of it came from dying stars. You are made of the universe. You are the universe experiencing itself. Think about that for a second. The universe created the conditions for stars. Stars created the elements. Elements formed planets. On at least one planet, those elements organized themselves into living things. Those living things evolved over billions of years into creatures capable of consciousness, of thought, of wonder. You can look up at the night sky and understand what you're seeing. You can trace your lineage back through billions of years of evolution, back through the formation of the Earth, back through the birth and death of stars, back to the Big Bang itself. You are not separate from the universe. You are part of it, a way for the cosmos to know itself. Scientists like Albert Einstein showed us that space and time are woven together, that gravity is the curvature of spacetime itself. Georges Lemaitre had the insight that the universe must have had a beginning, even when others doubted him. Edwin Hubble gave us the first concrete evidence that the universe is expanding. Stephen Hawking pushed the boundaries of what we could understand about black holes, quantum mechanics, and the origin of time itself. These thinkers and countless others built up our understanding piece by piece. They asked questions that seemed impossible to answer. They made observations that challenged everything people believed. They followed the evidence wherever it led, even when it took them to places that seemed absurd or contradictory. And we're still learning, still discovering. We don't know what dark matter is, but it makes up most of the matter in the universe. We don't know what dark energy is, but it's driving the universe apart. We don't know if there are other universes beyond our own. We don't know what happened in the first moment of the Big Bang before Planck time, when quantum effects dominated. But that's the beauty of science. It's not about having all the answers. It's about asking better questions. It's about building models, testing them, and refining them when new evidence comes in. It's about being honest when we don't know something. And even with all the gaps in our knowledge, the story we can tell is astonishing. From nothing, or something so close to nothing that it defies description, the universe burst into existence. It expanded, cooled, and evolved, created matter, light, and structure. It formed galaxies and stars. It made planets and life. It made you, and one day, billions of years from now, the universe might end. It might freeze into darkness. It might rip itself apart. It might collapse back into a singularity. We don't know. But right now, in this moment, it's alive. Stars are being born. Galaxies are colliding and merging. Planets are orbiting their suns. And somewhere on one of those planets, life is looking up at the stars and asking, where did all this come from? That question, that curiosity, might be the most remarkable thing the universe has created. You exist in a universe that didn't have to exist at all. You're made of atoms that were forged in the cores of dying stars. You live on a planet that formed from the debris of a stellar nursery. You're part of a galaxy that's one of hundreds of billions in the observable universe, and every one of those galaxies contains hundreds of billions of stars. The universe is vast beyond comprehension, ancient beyond imagining, and yet, here you are, a tiny part of it, able to understand it. You can hold the entire history of the cosmos in your mind. You can picture the Big Bang. You can imagine the first stars lighting up the darkness. You can trace the formation of the solar system. You can see the long arc of evolution that led from simple molecules to complex life to you. That's a kind of magic. Not supernatural magic, but the deep magic of existence itself. The fact that the universe is knowable, that it follows laws we can discover, that it's not random chaos, but an ordered, beautiful, comprehensible whole. And maybe the most profound thing is this: the universe created the conditions for you to ask why, for you to wonder, for you to seek meaning. Some people find that meaning in religion or philosophy. Some find it in art or love or service to others. And some find it in the simple fact that they're part of something so much larger than themselves, that they're connected to everything that has ever existed. You are stardust contemplating stars. You are the universe made conscious. And in this brief moment between the birth of the cosmos and its eventual end, you have the chance to look around, to learn, to wonder, to create, to love. That's what the universe has given you. So the next time you look up at the night sky, remember, you're not looking at something separate from yourself. You're looking at your origin, your family. The atoms in those distant stars are the same atoms that make up your body. The light traveling from those stars has been journeying through space for years, decades, even millennia, just to reach your eyes. You are part of an unbroken chain of events stretching back 13.8 billion years. From the Big Bang to the formation of the first stars to the birth of the sun to the emergence of life on Earth to this exact moment. Right now, as you wonder about it all, the universe was born. It grew. It evolved. It became you. And now you know how it happened. You know the story of the greatest journey ever taken. The journey from nothing to everything. From the first instant of time to the vast, intricate, beautiful cosmos we see today. This is your story. This is our story. This is the story of how the universe was born. And somehow, impossibly, wonderfully, you were there for all of it. In the atoms that make you. In the stardust that forms you. In the curiosity that drives you to ask, how did this all begin? The universe spent billions of years creating the conditions for you to exist. For you to wonder. For you to understand. Don't waste it. Look up. Ask questions. Seek answers. Marvel at the improbability and beauty of it all. Because you are not just in the universe. You are the universe. And the universe is in you.